Simple harmonic motion and phase. The video on simple harmonic motion shows us that the displacement x is equal to the amplitude a multiplied by the cosine of 2 pi times the frequency multiplied by the time from the start. This is when the start point is with maximum displacement, giving a graph something like this. We can also have this expression where we've replaced the cosine with the sine, and this is for when the displacement starts at the equilibrium position. So at t equals 0, we're in the middle. The video on simple harmonic motion and circular motion showed us that omega, or angular velocity, is equal to 2 pi times the frequency, giving x equals a cos omega t when we start at maximum displacement, and x equals a sine omega t when we start at 0 displacement. We can use a different expression which allows us to start timing at any point in the oscillation. If we start timing at epsilon radians from the equilibrium position, then the displacement at time t becomes a sine omega t plus epsilon, where sine of epsilon is given by the start position x naught over the amplitude a, and epsilon is called the initial phase, with omega t plus epsilon being the phase. For example, a body undergoes simple harmonic motion with an amplitude of 5 centimeters and a frequency of 3 Hz. Calculate the displacement of the body 0.7 seconds after it was 2 centimeters from the equilibrium position. Well, first we know that omega is equal to 2 pi times the frequency, giving a value of 18.8 radians per second, and sine of epsilon is x naught over a, which in this case is 2 centimeters, the initial displacement, over the amplitude of 5 centimeters, giving 0.4, meaning epsilon is 0.4 radians, making sure your calculator is in radians mode throughout these calculations. Now we get that x is equal to a sine omega t plus epsilon, and putting in the values given gives us a displacement of 4.3 centimeters. The positive magnitude of the displacement tells us that this is on the same side as the initial displacement of 2 centimeters. If it was on the opposite side, it would come out as negative. We can get a similar general expression for the speed v of an oscillator at time t when started epsilon radians away from the equilibrium position. And this is the expression. The speed v is equal to a omega cos omega t plus epsilon. For example, a body undergoes simple harmonic motion with an amplitude of 5 centimeters and a frequency of 3 Hz. This is the same example as before, but now we're asked to calculate the speed of the body 0.7 seconds after it was 2 centimeters from the equilibrium position. Well, we've already found that omega is 18.8 radians per second, and epsilon was 0.4 radians. So now we can put the values into this expression, again making sure our calculator is in radians mode, and we get an answer of 0.51 meters per second.